Hello everyone, I am Divya Srivavi, working as Assistant Professor in the Department of ECE SJBIT. In today's lecture, we'll be starting with Module 5, that is Quantization Process. A continuous signal, say for example voice, which has a continuous range of amplitudes and therefore its samples have a continuous amplitude range. In other words, within a finite amplitude range of the signals, we find an infinite number of amplitude levels. So it is not necessary in fact to transmit the exact amplitudes of the samples. Any human sense, that is say for example our eyes or our ears as ultimate receivers, it can detect only finite intensity differences. This means that the original continuous signal may be approximated by a signal constructed by discrete amplitudes selected on a minimum error basis from an available set. Means, if we assign the discrete amplitude levels with sufficiently close spacing, we may make the approximated signal practically indistinguishable from the original continuous signal. Amplitude quantization is defined as the process of transforming the sample amplitude m of nts of a message signal at a time t is equal to nts into a discrete amplitude v of nts taken from a finite set of possible amplitudes. So we assume that the quantization process, it is a memory-less and instantaneous process, which means that the transformation at time t is equal to nts is not affected by either or later samples of the message signal. This simple form of quantization, though it is not optimal, it is commonly used in practice. So Vk, it is independent of Mk and Mk plus 1. When dealing with a memory-less quantizer, we may simplify the notation by dropping the time index. We may thus use the symbol M in place of MNTS as we have indicated in the block diagram here. So the signal amplitude M, it is specified by the index K. If it lies inside the interval Ik, should be within the limit Mk less than M less than Mk plus 1, where K can take the value from 1 to L, where L is the total number of amplitude levels used in the quantizer. The amplitudes Mk, where K is from 1 to L, are called decision levels or decision thresholds. At the quantizer output, the index K is transformed into an amplitude Vk that represents all amplitudes of the interval Ik. The amplitudes Vk are called representation levels or reconstruction levels, and the spacing between the two adjacent represent levels, we call it as a quantum. Quantum or step size. Thus the quantizer output V equals Vk if the input signal sample M belongs to the interval Ik. V is equal to, it is given by V equal to G of M. and it is the quantizer characteristics, which is a staircase function by definition. Quantizers can be of two types. One is uniform or non-uniform type. In a uniform quantizer, the representation levels are uniformly spaced, otherwise the quantizer is non-uniform. So we consider only the uniform quantizers. Non-uniform quantizers are considered in some other topics. The quantizer characteristics can be of two types. One is mid-thread and another one is mid-rise. So this figure here, where the input-output characteristics are seen here, it is a uniform quantizer of mid-thread type, which is so called because the origin lies in the middle of the thread of the staircase graph. This figure, it corresponds to the input-output characteristics of a uniform quantizer of the mid-rise type, in which the origin lies in the middle of the rising part of the staircase-like graph. So here if we note that, you have to note that mid-thread and mid-rise types are of uniform quantizer and are symmetric about the origin. So this is a brief introduction about the quantization process. Next, let us understand what is quantization noise. So the use of quantization introduces an error defined as the difference between the input signal M and the output signal V. So this error is called as quantization error. So let us derive the expression for signal to noise ratio of a uniform quantizer. Let the quantizer input M be the sample value of a zero mean random variable M. A quantizer G maps the input random variable M of a continuous amplitude into a discrete random variable V. So their respective sample values M and V are related by the equation V is equal to G of M. In the previous slide I have explained this. Let the quantization error be denoted by Q, random variable capital Q, of a sample variable small q. So we can write small q is equal to M minus B. So when you take a random variable, it is capital Q is equal to capital M minus capital B. With the input capital M having 0 mean and the quantizer assumed to be symmetric, so it follows that the quantizer output V and therefore the quantization error Q also have 0 mean. A practical characterization of the quantizer in terms of output signal to noise ratio, we need to find only the mean square value of quantization error Q. So consider the input M of continuous amplitude, which is in the range minus M max to plus M max. Assuming a uniform quantizer of mid-rise type, we will find that the step size of the quantizer is given by delta is equal to 2M max by L, where L is the total number of representation levels. For a uniform quantizer, the quantization error Q will have its sample values which is bounded by minus delta by 2 to delta by 2. If the step size delta is sufficiently small, it is reasonable to assume that the quantization Q is uniformly distributed random variable and the interfering effects of the quantization noise on the quantizer input is similar to that of the thermal noise. So, we may express the probability density function of Q as 1 over delta or 0 otherwise. This is for this range. So, for this to be true, we must ensure that the incoming signal does not overload the quantizer, means the mean of the quantization error being 0, its variance is same as that of the mean square value. So, it is expressed as sigma q square, it is from the interval minus delta by 2 to delta by 2 q square fq of q dq. So, substituting fq of q is equal to q square, we will get after the integration it is equal to delta square by 12. So, typically the L array number, that is k, denoting the kth representation level of the quantizer, is transmitted to the receiver in the binary form. Let R denote the number of bits per sample which is used in the construction of the binary code. So, we may write now as L is equal to 2 to the power R. So, or we can also write this as R is equal to log L to the base 2. So, now we may get the step size as delta is equal to 2 m max by 2 to the power R, because delta is 2 m max by L. Now, I am replacing L with 2 to the power R. So, now the variance, it is sigma q square is equal to 1 over 3 m max square to 2 to the power of minus 2 R. Let P denote the average power of the message signal m of t. So, we may express the output signal to noise ratio SNR of the Q is equal to P by sigma q square, which is nothing but 3P by m max square into 2 to the power 2R. So, this equation shows that the output signal to noise ratio of the quantizer increases exponentially with increasing number of bits per sample R. Recognizing that an increase in R requires a proportionate increase in the channel bandwidth Pt, we thus see that the use of a binary code for the representation of a message signal provides a more efficient method than either frequency modulation FM or pulse position modulation PPM for the trade-off of increased channel bandwidth for improved noise performance. So we presume that the FM and PPM systems are limited by receiver noise, whereas the binary coded modulation system is limited by quantization noise. So the sinusoidal, when the system is a pure sinusoidal modulating signal, say for amplitude AM, it utilizes the representation levels provided. The average power for, if you assume a load is equal to 1, it is equal to AM square by 2. So the total range of the quantizer input is 2 times of AM, because the amplitude, message signal amplitude, it swings from minus AM to plus AM. We may set M max is equal to AM. So this equation sigma q square, it will be now 1 over 3 AM square 2 to the power of minus 2R. SNRO, it will be 3 by 2 times of 2 to the power of 2R for a full load. So expressing this signal to noise ratio in decibels, we'll get, this will be approximately equal to 1.8 plus 6 times of R. For various values of L and R, we can have different signal to noise ratio. Suppose if you have a representation level, if it is equal to 32, if L is equal to 32 and R is equal to 5, then signal to noise ratio SNR in decibels, it will be 31.8. Similarly, you have a table. If representation levels is 64, number of bits is 6, then SNR is 37.8. Like this the table goes on, and if the number of representation is 256 and R is equal to 8, then SNR is 49.8. So this is how we can find the SNR of for a uniform quantizer. So let me summarize what we have discussed in today's class. We have started with the quantization process. What do we mean by quantization? What is its block diagram? Types of quantization, that is uniform quantization and non-uniform quantization. In uniform quantization, you have two methods. One is mid-thread and another one is mid-rise. And then after looking into the waveforms, we understood what is the mid-rise and mid-thread type of uniform quantization looks like, and then we deduce the equation to find the quantization process for a uniform quantizer. What is its SNR signal, SNR equation? It is 3p divided by M max square into 2 to the power 2R, where R represents the number of bits per sample, L represents the number of representation levels. So for different L and R value, you have different SNR ratios. So after this, in the next video, I'll be discussing about pulse code modulation, its block diagram, step-by-step procedure related to pulse code modulation. Thank you.